All right, so moving right along. This doesn't look like it's going to have anything to do with classes, but it will in a minute. So I want to talk about the match expression in Scala. The first way of thinking about it is just as a better version of the switch statement. So over here you see we're having some character that comes from somewhere, and we match against that character. So here's the value that we want to match. Here's the keyword match. Then we have a bunch of cases. And so in each of the cases, we say what it might match, and then there's an arrow that says what should then happen. So it looks roughly similar like a switch statement in C or C++ or Java, except there's no break. And of course, in C and C++ and Java, when you had a switch statement, the break was always stupid. Did any of you ever want to fall through to the next case? Oh, yeah? So there's research where people would measure large bases of C code. And the default behavior of falling through to the next case is unwanted in about 96% of the time. So having a feature where the wrong thing happens 96% of the time is not a good language design. So the break thing, it doesn't really buy you anything, and it does buy a whole bunch of grief because, believe it or not, people do forget the break statements on a regular basis. So the Scala people said, these cases should be exclusive. It matches from top to bottom. As soon as it finds a match, it executes one statement, and then it stops. It doesn't keep on going to the next one. So you can have a default clause, and it's here very nice and uniform. Case underscore, an underscore means that would match anything at all. So that's instead of having an extra keyword default. Now, just like the if statement, or I should say, just like the if expression, if is an expression, and so is match, it has a value. So you can say ch match, and then instead of putting actions here, you just put values, and whichever value pops out, that is the value of the match expression. So here we would say the sign of something is, if it was a plus, it's 1, if it's a minus, minus 1, and otherwise 0. So that's the simplest way of looking at a match expression, but it really has many, many more features, so we'll go through most of them right now. The first one is you can capture the variable that's being matched. So you can say case ch, and that means this is an arbitrary match. Later we'll see how to refine it. And then ch is bound to whatever the match was, and then you can use it later in an expression. I'll come up with some examples. And so let me actually come up with this example first, because then it's easier to understand why this might be useful. So over here we'll say that case ch, if the character is a digit, so we have a test here, what's called a guard clause. It says you enter this part here if it's a digit, and we might want to see the ch here because we needed to use it in the test here. Now this makes most sense if you had a more complicated expression. Let's say that we had a function that returned something, and then I say match, and then I would say case ch if some property of ch. In this case, I really need to bind this thing here to a variable so that I later can use it here, because I don't want to call the function a second time. And so this is an often useful feature. There's just one minor nastiness with this, and that is that now we have a slight ambiguity. Over here, we had a case of a constant. Over here, we have a case with a variable. And in this case, it was easy enough to tell when it's a constant and when it's a variable. Right? This is obviously a constant because it's a literal. But what if the constant looked like this? Case pi. So if someone made a constant pi, there is in fact a constant pi. You can You can import from math. So if you imported everything from math by saying import math dot underscore, then uppercase p lowercase I is in scope. And now how does the compiler know that this thing means the constant pi, and this thing means match anything at all but bind it to the variable ch? And so the unhappy rule is that if the variable, if the thing that's behind the case, if it's not a literal, but if it is something variable, if it starts with an uppercase letter, it's deemed to be a constant. And so this is something that one has to be a little bit careful about, because there are odd cases where you do the wrong thing. This will happen to you once in a blue moon, and you will really hate it. There's a third kind of pattern. So far we've seen a constant value, literal or not. We've seen a variable that gets bound to stuff. And the third one is a variable colon a type, and then you match a particular type. So in this case, we want to match all integers versus strings. So in this case, obj must be some general object that comes from somewhere. I want to say if it's an integer, then we want to return its value. If it's a string, then we want to parse it. And if it's a big int, well, we have an integer result, then we make it as big as we can. So that's the somewhat artificial example here. So we match something in all of these cases. Oh, and if it's something else, an object of some other type, then we return 0. So notice that we have 3 forms that are of this type match, and they do exactly what you think. They say if it is an integer, bind it to the name x. If it's a string, bind it to the name s. If it's a big int, we don't care what the name is, so we just bind it to underscore. And finally, if it's anything at all else, we don't use it, so we also bind it to underscore. And so that's a nice feature. It's the equivalent of instance of in in Java. And I forgot what it's the equivalent of in C++. What's that? Type of? Okay, yeah, I haven't used that for years. So it does type inquiry, and it's nice because the syntax here is very uniform, right? You know that anytime you want to do such a lookup, you make a match statement, and you don't have to know special rules about an instance of operator. You just use essentially the same syntax. There's just a bit of caution that, again, the syntax here is very concise. So when you have something like this, variable colon type, that means you're matching against a type. But when you have just case big int without the variable colon in front of it, then you fall back to the first possibility, namely you're matching against a constant value. And that constant value is the companion object big int. Yeah?
If I just define a class, does it automatically have like an empty companion object?
I have no idea. I don't know. So that's a good question. So we have to try that and see if the match if it says, oh, there was no such companion object. There might always be one. So this has actually bitten me more than once. That for some reason I wasn't interested in binding it to a value because I was perfectly happy to just refer to it as obj. And so in my mind I said, if obj is a big int, and so I forgot to do the underscore colon. So be careful of this one. This one really happens. All right. So just to put parsing these corner cases to work. So have a quick look at this match statement here. So x presumably was declared as type any or object, and I don't mean what value can x never be. I mean what value can the match result never be. The value of the match expression. Okay, let's see what everyone's guess is. So, okay. So we have a pretty good collection of guesses. Most people said D, but there were a bunch of B's and C's and no A. So let's see. So could it be this case here? So this would be the case if F uppercase foo is a constant. Right, that could happen. So we could have a constant whose name was foo. Could it be the second case? Well, this would be the case if foo is a class and we have an instance of class foo. The third one means that it matches anything at all, provide, and then no provide anything, there's no if. It matches anything at all, and then it binds it to foo. It calls the result foo. In other words, foo and X would be exactly the same thing. So this can happen. And so by sheer elimination, it must be that the answer was D. And so what happens is these two things really mean the same thing. They both mean bind to a variable, and they get executed top to bottom, so this one will happen before that one. In fact, has anyone put this into a worksheet? I have no idea whether this will, in fact, give you an error, because the compiler ought to realize that this thing can never happen. So try that out afterwards. So the key here is that underscore is a variable. Foo is a variable. Underscore is just a variable that you don't use anymore. And so since they get executed from top to the bottom, that one can't happen. All right, so you have this minor weirdness that you have to decode which of the three cases you have. Constant match, type match, variable match. And you have, not to forget, this very useful guard clause that you can put in if here. And that one uses that all the time in practice. All right, so you might say, what does that have to do with classes? There are many situations where we have recursive data types, such as lists and trees, where one does this pattern matching stuff all the time, and there is a way of making classes for it that are optimized to work well with pattern matchings. And they're called case classes because you can use them in these case clauses of a match statement really easy. So when you have a case class, you declare it by saying it's a case class. And a case class is just like a regular class, except that you get a bunch of methods at no charge. Those methods are apply. That's the one in the object that you don't have to worry about writing new. Unapply we'll see in the next couple of slides. ToString gives you a standard representation of this, equals hash code, and a thing called copy that we're not going to talk about now, but I'll give you some material where you can find out what that does. So case classes give you these kind of standard classes, and we'll see in a minute what it means that they can be matched in these statements. So you have an example. So I have some abstract amount, abstract class called amount, and now I have subclasses. These are all amounts. Notice that amount is not a case class, it's a regular class, but these subclasses are case classes. So they're just declared with this magic word case. And first of all, that means that if I wanted to have one of them, I could just say, give me $5. I don't have to write new because the apply method is automatically provided. Also, it means that when you print it, it shows up as $5. I don't have to define ToString. It's given there for me. So those are nice things, but it gets much better than that. What I can do is I can say if I have some amount and I know that this thing belongs to this abstract class, then I can make a match and say, is it $1 of some value v? Or is it a currency of some value x where the second component is the string chf? Or is it this value nothing? So I can use the names of the classes here in the left-hand side of the arrows, and then they get automatically destructured. So when I have a particular amount, then the v here gets fished out. The x gets fished out here, and the if clause with the second match gets automatically generated. So that's super nice, and it happens a lot in these applications. And that's what a case class does. It gives you the possibility of using the names of the classes on the left-hand side of the case. So let's have a practical example. So in Java, one often uses null to indicate that a result doesn't exist. So you'll often see a method returns maybe a string, or it returns null if it couldn't find an answer. Say you're looking up a username. You have a username and you want to look up the the password for that. You might write a method like that. But null is actually not a very good choice, because it often happens that programmers write for the happy scenario, and then much later during testing, those nulls creep in, and what happens? You get a null pointer exception, and your program dies a sad death, right? In C++, of course, what happens is worse, and we don't even want to contemplate that, right? So, but nulls are not generally safe, because people are not usually very good about thinking about nulls when they write the normal scenario of the program, and then later you have to find out those corner cases by testing. So it would be nicer if there was an alternative where during compile time one can see, did the programmer worry about the corner cases? And so in Scala, that type is called option. So option is a wrapper around a type T that says it's a type that either has a value or it's not. Option is a superclass with two case classes as subclasses. There's a case class called sum that wraps a value, and there's a case object called none. A case object means it's a case class with just one instance. Now that's called none. That indicates that there was no answer. So as an example, the map class, I guess, is it a class? Is it trait? Whatever it is, the map type has a method get that returns an option, because it's possible that when you ask get on a key that there is nothing there. So it gets an option of the value type, which is either sum v or it's none. So let's have an example here. So we have a map, and now we're looking up a key from this over here. And there's two possibilities. That's where the match comes in. Either it is sum of something, and here I call it score, and then I can get this thing bound to this variable, and I can use it. Or the answer is none, and then I would react to that by doing whatever. So you can see option is a case class, or I should not say that. I should say that option is the superclass of two case classes, and then I can use this match statement to figure out which of the two it is. Now, it's a nice example of a case class because it shows you have two cases. But it may not be a nice example for match, actually, because if every time you had to use a match for this, it would be a little bit tedious. So I don't want to give you the impression that when you have an option that you must use the match statement. There's a couple of convenient shortcuts. It oftentimes happens that you are in a situation where you want to get something, and then when it's not present, that you're willing to take some alternative. So there's a thing called get or else on an option. So when you call get or else on an option, it either gets the value as the value and it unwraps the sum, or if it wasn't a sum but a none, then it gives you this alternative. And in fact, in maps, that is so common that the map itself has a get or else. So the takeaway is that option is a useful class. You can always extract it with a match statement, but if you're in a situation where you happen to have a default value for none, you don't have to use the match statement. So we've talked about this before, that you can, when you do the extraction of any, here I'm using a pair. So before I was using a case class, and it works as it happens. A pair or a tuple 2 is a case class. I can have this nifty test for values. So you've seen that before here, where I can say I want to have something where the second part is a CHF. I'm doing the same thing here, and I say I have a pair where the second part is a 0. I could also write this, of course, if I wanted, by saying it's a case of x or xy. if y is 0, but that's a more cumbersome notation for the same thing. So this syntax here is very nice. Sometimes you're in a situation where you don't care what the second part is. You want to use the first one, and the other stuff you don't care. So here I'm saying, is it a vector with two components, where the first one, I want to use it, so I'm calling it x. The second one, I don't care what it is. I put an underscore. And very occasionally it happens when you have a constructor that uses a variable number of arguments, such as vector, that you want to match the entire tail. And so I'm going to give you the syntax now because we're going to be needing it in a couple of units. And so first of all, to match an arbitrary sequence, it is underscore star. That's just a special thing you have to remember. Yes?
Is this a new feature of Scala? Because in my day we used to just do x const xs.
No, that's different. When you use the const stuff, that matches lists.
Yeah, or like.
But with a list, that's a specific match. You match the head against the tail. Here you have an arbitrary sequence of tail things. So I don't think you ever use this feature. You use it in practice a lot because in practice you often use data structures that can be constructed out of an arbitrary set of things. But when you use lists, that's the tail is a single thing. And we'll get to that in the lab. But so you will run into this, and then you will remember to look up the slide. So the syntax for an arbitrary tail end of a variable set of arguments is underscore star, which looks reasonable enough. And every once in a while you run into the situation where you want the tail by name. You want to give it some kind of a name, and then you can get to use the syntax x at underscore star, and you will absolutely forget this every single time when you need it, and you will need to look for it. I used to have to look this up on Stack Overflow every time, and the only remedy that I had is to write my own book so that I could look it up in my book instead. But it's a useful syntax in those circumstances, and when it comes, I'll show you. Yeah. All right. So notice that this syntax here, where you could do this matching here, works for pairs. It works for case classes. It works for vectors, which are not case classes. When you look them up, you'll see that a vector is definitely not a case class. And so there is a generic mechanism where any old class can say, I want to be usable on the left-hand side of an arrow in a case statement. You have to provide what's called an extractor. In a case class, the extractors are provided automatically for you, but if you want to do this in general, you can write your own extractors. The extractor is kind of the opposite of what the apply method does. Recall what the apply method does when you define class name, parentheses, args, then it constructs a new object of this class by calling new on your behalf. So it turns args into an instance of the class. Now we want to do the opposite. We have an instance of the class, and we want to recover what the args were. That's what extractors do. So I already have a point that comes from somewhere, and now I want to know what x and y would give me the same point, because that's what you need in matching. You have an object, you match that object, and then you want to say what x and y's would have given me that object. So you can do that in any class that you want by defining a method with the secret name unapply. So just like apply is hardwired to call the parentheses, unapply is hardwired to take an object apart into its constituents, into the parameters that when you would have fed them to apply, you would have gotten the object back. So it gets an input. The type of that must be the type of the thing that you want to unapply. And you return a tuple of the parameter values. So here, input x, input y, in the case of making a point. If you were to make something else, it would be a more complicated thing. And you need to wrap the tuple into an option, because it's possible that the match might fail, that you might have an object that you don't know how to reconstruct. For example, with points, that doesn't really happen. With points, every point that you have has an x and a y. But you might have enforced something. Let's say you had a class fraction, and in the constructor you enforced that the denominator can't be 0 by the require thing, for example, that you saw in the previous slide. Then when someone gives you a thing with the denominator 0, you might want to say, well, there's no possibility of having obtained that, so you want to indicate that lack of a match. And that happens by you're returning an option of the tuple. So you return a sum of the match, and in the oddball case that doesn't happen, then you could return a none out of unapply. So that's what unapply does. It is totally unintuitive, I think. And I have to, again, it's something that when I want to do is I have to remind myself every time exactly what the mechanics are. But the idea of unapply is it makes it possible to do these matches in all possible cases. So going back one more time to the intuitive class situation of the case classes. In a case class, these case classes, they can be easily constructed out of these things, and it's totally obvious that they should be usable in this way. And the unapply mechanism generalizes this to arbitrary classes in case you need that. All right, so here we have a fun exercise for apply and unapply. So I want to know how many of these statements here are valid statements. So I should tell you that tuple 2 makes a pair, and yes, it's a case class. I have an answer. Okay, yeah, you can all turn around and see what everyone else says, because everyone has a different answer. Okay, could you guys commit yourselves to some answer? You have an answer? Okay, so let's see the first one here. That one is correct, right? And it sets T1 to the tuple 3, 4. And it's correct because tuple 2 is a case class, and so you can use the name of the class. The apply has been provided for you. The next one is also correct. T2, it's also the tuple 3, 4. Because new, it's just a regular constructor. Whether you use the constructor or not, that's up to you. But you provided the shortcut if you want. The third one is also correct. It calls the apply method on the tuple 2 companion object. And that is just the long way of saying the first line, which calls the second line. So this also sets it to 3, 4. The fourth one is not correct because new tuple 2 is an object of type tuple 2. And a tuple 2 object doesn't have the apply method. The apply method belongs to the tuple 2 object. Okay, I didn't say that very well at all. So if you have an object of class tuple 2, that one doesn't have an apply method. The companion object, that single object that is a companion to the tuple 2 class, that one does have the apply method. So you can't invoke apply on this one here. All right, so the next one here, val tuple 2 x, y is T1. That sets x, y to 3, 4. Well, what it really does is it sets x to 3 and y to 4. That is the use of the extraction. Right? That's exactly what extraction does. On the right-hand side, you have an object of type tuple 2. On the left-hand side, you have the name of the class plus a bunch of variables inside, and then it extracts one by one, setting the first one to the first result of the unimply call, and so on. Let's see the next one here, val tuple 2. That one looks correct.
Doesn't unapply return a sum? Object of type sum?
Thank you. So this one is wrong because unlike with apply, where you were perfectly able to call it, you cannot call unapply. Then that doesn't work because this thing means to first execute the call to unapply, which returns a sum, an SOME, and it's a syntax error to say tuple 2 equals a sum. So that one is wrong. What about the last one? That one is perfectly valid. What now happens is that T5 is that object, that sum object. I should have had another one. So this one is correct. And it sets so T5 equals sum of the tuple 3, 4. So the correct answer was B. Okay. Now what I should have done is I should have added another interesting line to this. What if I say val sum of T6 is tuple 2 dot unapply Yes, that'll work just fine. Because what is the thing to the right? The thing to the right is sum of the pair 3, 4. It's a case class, and so the extraction will work perfectly. This will match T6 to the value of the tuple.
I thought the extraction only worked on tuples.
No, the extraction works on anything that's a case class, or on a class where you have defined the unapply method. But that's not all. Even this will work. It'll set T7 to 3 and T8 to 4.
Didn't you say that unapply, like, applied to inside the matching?
It works in both cases. So if we look at the slide here, It works in the case of matching, which is what you see here. But it also works in the simple case of an assignment. And both situations are useful. Okay, so that's, of course, a completely artificial example. The only thing that's kind of interesting about the last example is that you can nest the matching as deeply as you want. And that really is sometimes useful. So if you have a nested data structure, you can say, I want to have this part of the structure matched with some constants and with some variables. And so the code to achieve this is actually complicated, but the notation is very compact. Finally, as the final technical wrinkle here, when doing that extraction, in the fairly common situation that unapply yields a pair, a true tuple, then you can use an infix notation for the class. So instead of saying case point of x, y, you can say case x point y. Now, why would you ever want that? It's not really meant for points, of course, but it's specifically meant for lists and such. So with lists, you want to take them apart by matching the head against the tail. As you'll see in the lab, one constructs this kind of lists by having a head that's something and a tail that's, again, a list. And we want to be able to say case head colon colon tail, because it looks pretty and it's intuitive, right? Case of a list that has this head and this tail. And to make this work, they've come up with this bizarre rule that says that if this thing in the middle is the name of a class whose unapply method returns a pair, then this will work. So colon colon is actually a class. Classes can be named anything at all. They can have these symbolic names. So there is a class called colon colon with an unapply, whose companion object has an unapply method that does this. And so this is particularly useful when you match a bunch of things. So when you match like first colon colon second colon colon rest, because colon colon binds right to left, since it ends in a colon, that's where the rule comes from. That rule was specifically made because colon colon is such a nifty way of smashing lists together. That's how it works. Surely this will make no sense at this point, so there's a lab that makes you do it. All right, so in the lab, what I'm going to have you do, just because it's a good exercise and you see what goes on, is I'm making you reinvent the option type, but only for doubles. The reason for that is that we haven't yet talked about how to write generic types. We'll see that in the next module. So, and that's pretty straightforward. I'll have you reinvent the list type, but only for doubles. And before getting into the weirdness with the colon colon stuff, I'm saying make the list type as a case class with two cases, nil, which is self-explanatory, and cons, like it's called in many languages. And then do the colon colon stuff and see how that works. And finally, as a more practical application, I'm not sure whether you're going to get to this, is to model expressions. And so this is a very typical application of case classes that happens when you write compilers or something, that you say an expression is made up of what? An expression has an operand. In this case, we'll just use a string for simplicity. And then it has arguments. And each argument could be another nested expression, or it could just be something more straightforward. So we say an expression is a number or an operation. An operation has an operand and more expressions behind it. And then it's trivial to write a function that evaluates such expressions. So go ahead and do that so you get a feel of how to work with these in a more practical setting. All right.
Just have a question
Yes.
regarding like @_
Yes.
star. Like for sequences, I just tried and like what's the difference between that and putting x plus column xs? Because it works and it gives me a sec, so it's
Okay, so let's try this for a vector. Let me see if I can get a worksheet here somewhere.
because I think plus column is the cons of sec.
hang on. Where have So let's say we do this. Okay. Then you'll get a match error because it doesn't have exactly two values. Now we'll say t at okay, now I still get a match error? Hang on.
Maybe it's because it's only printing.
So it doesn't seem to.
Doesn't flush
Oh, it doesn't have print on? That may be true. There we go.
But is that faster than putting H plus column and then T?
Okay, so say again.
Case
Yes?
H, no vector. H plus column, and then T, just T.
That's T?
And then print T.
That works?
Yeah.
I had no idea that works.
And plus column is like cons, but for sec. It works for all subclasses of sec.
That is interesting.
So
That looks nice. Okay, so plus colon must be a class. Okay. That's good. Let's see if it's a class. Maybe it's an abstract class. This is good. I have never thought about it, so I have to think why it even works. Where do you think plus colon is defined?
I found it while reading the Scala doc of sec.
Okay, so there is a sec. Okay, let's find that out. I don't have the Scala doc here.
That's that before.
Okay.
It's defined as def, so
Oh, no, so I know the plus colon function, right? This is the plus colon function. I don't understand why it matches against it. Because you can't match against an arbitrary function. That is a very good question why that works. Right, so what you have is no, it was here. So you have this expression here, right? And the only way that something like this works is if this thing is a class name and it's the infix notation, but I've never seen that class.
can't it be an operator?
No, it can't be an operator. I mean, you can't, like, for example, there is a. Let's find another one in sec that there is like plus plus equals or something. Like there's a plus plus colon, for example, right? And it can't be, that will not compile, I'm quite sure. Right. So there's something special about plus colon. Right, right. So someone somewhere must have defined a plus colon class. Can you find it?
But for plus column, you find
Right.
an
But-
object.
Yes, exactly.
And
Where?
in the Scala doc, just search in the corner.
Let's find it.
Description is an extractor used to head tail deconstruct sequence.
Plus colon. Beautiful. Okay. Yes. Okay, it's an object and it has. Oh, that's why I couldn't say new. So if I just look at plus colon in the REPL or in the. Where did I have it? Here. Yeah, here it is. Okay, yes, it's very nice. All right, so this is the exact same thing, and so I agree that's nicer than doing this stuff. And so I guess they must have found this ugly enough that they added this class. So I'll have to find some other example when this one doesn't work. So I'd have to find some class that is not a sequence, but that also has a var args parameter. This happens in practice when you do XML, which we will do in a couple of labs. So although now that I think of it, that it's a node sequence. That's a sequence too. So I may be able to not do that. That would be good because it is an obscure operator. The other time that it happened to me is when you write a recursive function with a variable number of arguments. Okay, but that's good. So in that case, dismiss this from your mind and use plus colon. That's nice. It's consistent.